We're going to consider a non-homogeneous linear differential equation written very generally as Ly equals f. That if f, the thing on the right-hand side, is a function that corresponds to a solution to some constant coefficient differential linear equation, then we can solve it with undetermined coefficient. What happens if your right-hand side is not a form of a differential equation solution? So for example, if you pick tangent of t is not the solution to some constant coefficient linear problem. So the undetermined coefficients method is not going to work. We need a way that can come up with a solution in general, regardless of what's on the right-hand side. To try to motivate this, we're going to come back and look at our good old first order linear differential equation and talk about that integrating factor method. Now remember, the general solution to a problem like this is always going to be comprised of a homogeneous solution and a particular solution. Okay, so the homogeneous problem is essentially take the left-hand side, set it equal to 0. This is a constant coefficient problem, so we know that the solution has to be an exponential. You put that in, you'll find that lambda is -a, so you'll know that the homogeneous solution is some multiple of e to the -at. Now we're going to turn to integrating factors to talk about how to find the particular solution. Now the integrating factor, when we multiply both sides of this equation by the integrating factor, it has the wonderful property that it will turn the left-hand side into a perfect derivative. And it will be a perfect derivative of the integrating factor times the function we're looking for, and we'll get this. Now, generally we can apply the antiderivative or the indefinite integral to solve this problem, so instead I'm going to try something slightly different. Rather than taking every antiderivative, we are going to talk about one particular antiderivative. And so we can antidifferentiate this, but we can say, all right, it will choose the antiderivative that has some t0 as its starting value. All that's going to do is set the value of that arbitrary constant to be one specific out of the infinitely many. Now we have to be a little bit careful about dummy variables. When we have the upper limit of integration as a variable, we have to make sure that the dummy variable inside is a little different. This is going to allow me to write the expression kind of like so. And I'm just choosing s as the dummy variable here. Now, because t is a constant with respect to s, I can pull this inside. And what will end up happening is that I will end up with an expression that looks like this. And this is what I'm going to take to be my particular solution. This thing right here, I'm going to abbreviate as G, capital G of t and s. It's a function of two variables, t and s. It depends on the information from the left-hand side of the differential equation because there's an a there. I'm going to call this the Green's function for the differential operator derivative plus a, the left-hand side of my first-order problem. Using a method we've already seen before, we can write the particular solution in terms of an expression that looks like this. Now, I really like this expression because it's got the right-hand side function all by itself right here. So once I've determined the Green's function, all I then need to do is plug in the right-hand side, find the antiderivative, and I'm done. I have come up with a particular solution. If I want to switch the right-hand side, no problem. I just plug it back into this integral, I integrate again, and I'm done. And note, the choice of t0 is irrelevant. You will always still solve the problem regardless of this choice. This kind of seems like a nice, convenient thing to do. Can this be done for a higher order problem? And what we're going to do is we're going to take a look at just our second order linear differential equation. It will have variable coefficients at worst, because we want to be able to come up with a method that will work for a variable coefficient problem. And we're going to call this side L of y. I want to let the particular solution be defined according to this antiderivative, this function here. And I would like to build it exactly the same way. Can this solve the DE? What conditions do I need? Now, what we need is a technical result. We are going to need something called Leibniz's rule. Leibniz's rule says if you ever need to differentiate a function that's been given in this antiderivative form, and it's a function of 2 letters on the inside like this, it will turn out that you have to properly account for everything in this way. And so that's fine. So the idea is we are going to differentiate this expression for y p of t. We're going to sub it in to the dE, and then we're going to try to find conditions on g, and then we're going to try to find g. So here again is our integral expression for the solution, the particular solution. Remember, I'm assuming that I can always find the homogeneous solution. So if I want the first derivative, which I'm going to need because I need to substitute this into the differential equation, I have to differentiate this entire expression. And Leibniz's rule is going to say that, okay, the thing inside my integral that has 2 variables, in my case, it's going to be this. So I'm going to write this as g of t and t, and I'm going to write it in purple. Why are you doing that? Well, I'll show you in just a moment why that's going to be the case. And then this is going to end up giving me t naught to t, partial derivative there, because the function f does not depend on t, so effectively it can be removed. Now, if I want the second derivative, I'm going to have to differentiate all of this stuff. So I have to differentiate all this stuff that I've color-coded in purple for some reason. And then I'm going to have to differentiate all of this stuff again. Now, this will be slightly different because I've got a partial derivative in there, but it won't matter. I'm still going to apply the Leibniz rule all the same. So when I do this, I will get a partial g with respect to t here, all in purple, times f, plus g of t and t times an f prime of t. And then I'm going to apply the Leibniz rule one more time, and I will get dg dt, both variables set at t, f of t, and then I will be able to pull the derivative inside. It will apply to the stuff on the inside. Because the f does not depend on t, this will end up being a second derivative like such. And that's what I'm going to get right there. Okay, so when I sub it into that differential equation, I'm going to get the purple stuff, dg dt, f of t plus g t and t, f prime of t, plus this red term, dg dt, f of t, plus the antiderivative, second derivative with respect to t right there, and so on and so forth. So I put all of that in. That's going to be y double prime. Then I'm going to have the y prime term. So it's going to have this p of t. And if I scroll back up, I'll have another purple term, g of t and t, f of t, plus this antiderivative there, where that's one partial derivative, f of s ds, and then I will add to that q of t. So this is the term with my original guess, t and s, f of s ds. And I want to set this equal to the right-hand side. So I'm going to regroup things here. And in particular, everything that has an antiderivative and integral, I'm going to put together. So I'm going to combine everything that has an integral and combine it together. The other thing I want you to note is that if there's a function of t in front of one of these integrals, I can pull it in. If there's a function of t in front of one of these integrals, I can pull it in because the integrals are just functions of the dummy variable is s. So at the end of the day, I'm going to get this. The second derivative with respect to t, p times the partial with respect to t, q times this function. All of that stuff is going to be is going to be multiplied with f. And then I'm going to put in all these other terms. I will have this dg dt, f of t plus g of t and t, f of t. I'll have a red term, f of t, and then I'll have another one of these purple terms that pops up, p of t times all of this stuff, g of t and t with an f prime of t. And I want that to be equal to f of t. What conditions do I need in order for the left-hand side of this thing to match the right-hand side of this thing? Is I'm going to make sure that this quantity here in the square bracket, I'm going to have that g satisfies the homogeneous differential equation in the t variable. So what I mean by that is I want this second derivative of g plus p dg dt plus q g of t, I want this to be equal to 0. So I'm trying to get rid of that integral term. And now here's where the color coding comes in. In order for all of this stuff to go away, I'm trying to get rid of everything in purple here. Now initially the purple came about because of the first derivative. So if I set this equal to 0, this will eliminate the dg dt term that came from yp. Because if that was 0, there was no way I could have differentiated it to get there. So if I had set that equal to 0 earlier, that would be gone. And then the final thing that I'm going to do is deal with this red term. Now you can see that I want this term in red to just give me an f of t. So I'm going to set this dg dt equal to 1. These are the conditions on g that will make yp of t a solution to this differential equation. Number 1, g has to satisfy the homogeneous equation. Number 2, we are going to say that whenever you set the two variables equal together, they be 0. And number 3, we are going to say that if you set the variables equal together in the partial derivative, it makes it 1. Because it solves the homogeneous equation, it has to be some sort of linear combination of the fundamental solutions to this Ly equals 0. So normally when we have a linear combination, we would just say, oh, take some multiple of the first solution and add it to some multiple of the second solution. But the trick here is that there also has to be a function of s. So in order to bring in some sort of s dependence, I'm going to make an interesting guess. I'm going to say that these things are going to be functions and they're going to be functions of s. So I'm going to call it u1 of s and u2 of s. So this is what's called variation of parameter. Now, we are going to find u1 of s and u2 of s by using those other two conditions. So g of t and t better be 0, and the partial derivative with respect to t of this function of t and s, when I plug in s is equal to t, that had better be 1. I'll have u1 of t, y1 of t, plus u2 of t, y2 of t, better be 0. And because I'm doing a partial derivative with respect to t, the only parts that will get affected are the parts that start with a t. So then this will be u2 of s, u times this derivative, and that'll be equal to 1. But because I have to plug in s is equal to t, so that'll be a t, and that'll be a t. I'm going to get a system for u1 and u2. It'll have a y1 t, y2 of t, y1 prime of t, y2 prime of t, a 0 and a 1. I can row reduce this. I'm going to multiply everything in row 1 by y1 prime. And then down in the bottom, I'm going to multiply everything by y1. I'm going to try to make a pivot underneath. y1, y1 prime, y2, y1 prime is 0. Negative of the first row added to the second is going to give me this. And then I'll have y1, y2 prime minus y2, y1 prime, and I'll get a y1. 1, y2, y1 prime, y1, y1 prime. Those will cancel. I'll get a 0. And I'm going to call this thing w. So I'll get a 0, a 1, and a y1 over w. I'm going to multiply the second row by negative y2 over y1, and then add it to the top one. That's going to give me y1 over w, negative y2 over w. So what this result tells me is that u1 of s is going to be negative y2 of s over w of s, and y2 of s is going to be y1 of s over w of s. So this Green's function was u1 of s, y1 of t, plus u2 of s, y2 of t, negative y2 of s, y1 of t, plus y1 of s, y2 of t, all over w of s. You can call it y1 of s, y2 of t, subtract y1 of t, y2 of s. And downstairs, I'll have a y1 of s, y2 prime of s, y2 of s, y1 prime of s. I call it w because it's the Wronskian. Right? This is the Wronskian of the fundamental set. And I know that the Wronskian of the fundamental set is never going to be 0. If I define the Green's function like I did above there, so t naught to t, this will be the particular solution. So this is the general most YP. It applies for any f.